Swayam Prabha. Digital India. Educated India.
We have seen that determination of the natural frequencies and the natural modes of multi-degree freedom system are quite computationally intensive, particularly when the number of degrees of freedom increase. But in many situations, the designers will be happy to have some approximate idea about the fundamental frequency, that is the lowest natural frequency. So, in this lecture, we would like to present techniques of quickly and approximately finding out the lowest natural frequency. There are quite a few methods, and we would like to discuss two methods. One method which will give us the lower bound, that means the actual natural frequency of the first mode will be higher than the value we find, and another method by which we will get the upper bound. That means the value of the actual natural frequency will be lower than the approximate value we get. So, therefore, if we apply both the methods, it will be possible to get quickly a band, and the actual natural frequency will be within that band or that range, and that can sometimes be very useful in the design stage. The first method which we will discuss we call Dunker laser. We will take up a particular case as an example, but whatever we discuss and derive will be quite general, as you will realize. So, let us take this 3-degree freedom system. So, for this particular system, for example, we can find out the influence coefficient. Now, one thing it is perhaps clear to you that there will be two kinds of situations while finding the flexibility matrix and using the influence coefficient approach. The cases which we solve, like these masses are there, but the other end is free, those cases are relatively simpler for finding out the flexibility matrix, because they are statically determinate. We can just apply the load anywhere, immediately we know the load under which each individual spring is subjected. But a case like this, when this end is also connected, it becomes statically indeterminate, and still it is possible to find out the deflection by applying unit load. Only thing that it is slightly more involved, and therefore, I think one has to be careful. So, the influence coefficients are A11, are Aij. Now, what we do, we know that under normal mode oscillation, each coordinate or displacement can be written as xi or xi, and say the mode is jth mode, is equal to xi, the jth mode, cosine omega j. That means all the I varying from 1, 2, 3 for the 3 stations, and j is a particular natural mode. So, in this case, we will be mostly concerned with the fundamental frequency in this approximate method. So, we may consider this to be 1, and now onward, for the sake of simplicity, we will not put the superscript, but we will understand that what we are writing, it represents the first natural frequency or the first mode of oscillation. So, we can write that xi is equal to capital Xi cosine omega t. Omega obviously is then the first natural frequency, because that is our concern now. So, x2 dot I will be minus omega square xi cosine omega t, and the inertia forces at each station Fi will be equal to, say, this I we should not mix up with inertia, so we may call it as F. So, it will be then minus mi xi 2 dot at the station I, which then will be nothing but omega square mi xi cosine omega. Now, we also know that all the stations, all the masses, they reach their extreme position either way at the same instant when their velocities become 0, and of course accelerations become maximum. So, maximum inertia force equal to omega square mi x. So, at this instant, the deflection at the ith location will be due to all these inertia forces, because there is no other external force acting. So, therefore, it will be omega square mj xj aij. This is the force, maximum inertia force at this instant at the jth station, and the deflection at the ith station due to this force at the jth station is to be multiplied by aij, and this we sum up from j is equal to 1 to n is the number of degrees of freedom. In this particular case, n is equal to 3. So, or this we have done. So, the equations will be or mj aij mj minus 1 by omega square into not in this, I will expand it and write here. So, for 3 cases n is equal to 1 to 3, what will be the equation in expanded form? M1 A11 minus 1 by omega square follow the same kind of thing. So, it is the same set of equations which we have derived earlier, and you all understand now that a non-trivial solution will be possible with the determinant being 0. So, for non-trivial solution, the determinant should be 0. This we have done earlier. So, now if we write the determinant, the characteristic equation becomes like this. It becomes 1 by omega square to the power 3 plus A11 we need not go to the higher term. So, for the general case, at n degree of freedom system, this will become 1 by omega square to the power n So, we have not derived it, we have just tried to extrapolate, but one can easily do the whole calculation even for the n degree of freedom case, and the characteristic equation, the first 2 terms will be like this. Now, if the solutions of these equations are the natural frequencies of the system. So, if the solution which represent the natural frequencies be the omega n1, that is the first natural frequency, omega n2, that is the second natural frequency, and so on. Omega n3 is the third natural frequency in this particular case, and in general it will be omega n. Then these are the roots of, that means the 1 by omega n square, 1 by omega n2 square, 1 by omega n square, these will be the roots of this characteristic equation. So some of the roots we know we can write like this. We already know that the sum of the roots, so 1 by omega n1 square plus 1 by omega n2 square plus, for this one say, omega n3 square will be equal to this is a known result of algebra, but one can easily do this by this technique. That means this equation for 3 degrees of freedom, then it becomes what? It becomes 1 by omega Now, this is an equation of the same order, and if we expand this, now the roots of this equation are very obviously this, this and this, and so therefore, this equation is same as the characteristic equation for 3 degrees of freedom system. That means that equation will be same as this, and when you compare these two equations, you will find that first term will be same as this, second term whose power is 1 by omega square to the power 2, its coefficient will be this. That we can easily, from that the coefficient will be in this, the coefficient will be this, and that equation coefficient is this. So therefore, these two must be also same. Now comes the main logic of Dankarle. Generally, omega n1 is much less compared to omega n2, which is again much less compared to omega n. Generally, they are gradually increasing. So, 1 by omega n1 squared is much less than, sorry, much more than 1 by so therefore, in this term, this is the largest term and compared to these two. So, is approximately equal to, that means these two terms can be ignored since they are much smaller than this, and this of course then we can write approximately equal to so for a general case, Dankarle's equation says that the fundamental natural frequency that means 1 by omega n1 square is approximately equal to a I m I equal to 1. So, from this we can calculate the fundamental natural frequency approximate value. Now, this value is going to be what? Upper bound or lower bound? Now, we can see here that of course, this 1 by omega n square is obviously real 1 by omega n square is less than this, because two terms we have ignored. We have assumed this whole thing to be 1 by omega n 1 square. So, the real omega 1 by omega n 1 square actual value will be less than this. So, when you take the inverse, the actual omega n 1 square will be more than the value of omega n square what we get from here. That means this is nothing but a lower bound. That means we can say that the real natural frequency for the first mode is never going to be less than this. It will be always more than that and approximately equal to this. We can apply this to our one example we have taken. Let us see that how we get what kind of value. Let us take the example. Let us take the same problem which you have already solved. So then you can compare the result. This is a problem which we have solved, and its first natural frequency, if we remember, is equal to which we found out by matrix iteration method, and which if it is done accurately it will be an exact value. Now, let us apply this. This is x1, this is x2, and this is x3. So, what will be A11? We have already found out earlier, but let us find again. A11 is the deflection of station 1 when unit load is applied to station 1 itself. So, it is nothing but the stretch of the first spring. So, it is this, and this will be also the deflection of at station 2 due to a unit force at 1, also deflection at, because this shifts just like a rigid body. And again we know the deflection at here due to unit loads here and here are going to be same. And that is why actually the flexibility matrix is a symmetric matrix, as you can see. A22 is equal to stretch of this spring plus stretch of this spring. That will be the deflection here if a unit load is applied at station 2, and this is 1 by k plus 1 by 2k, and that is 3 by 2k, and A33, because we will not require others, we will require only A11, A22 and A33. This will be 1 by k plus 1 by 2k plus stretch of this spring 1 by k, which is equal to 5 by. So, by Dunkerle's approach, which is this 1 by omega n 1 square is approximately equal to A11 m1 plus A22 m2 plus A33 m3. We also know m1 is equal to m, m2 is equal to 2m, m3 is equal to something. So, this will be equal to A11 is 1 by k into m, which is simply m by k. A22 is 3 by 2k and this is 2m, so it will be simply 3m by k plus A33 is 5 by 2k and m3 is m, so it will be 5m. And this is equal to 2 plus 8 . This will be 2, this will be 6, 8. If we find out omega n1 from this, we will get square root of 1 by 6.5 is 0.4. So, when you compare this result with the actual value is here. So, we find that this is slightly lower than the actual value, but we find it is quite close. It is 0.4 here, here it is 0.425. That means the difference is in the second decimal place. That too again not much, you can calculate the percentage error, and also that point is revealed here that it is a lower bound. That means the real value is above this. So, you can see that this is a very quick method of estimating a very approximate value of the fundamental frequency of a system, because calculating the influence coefficient, if it is generally very simple. If the case is statically indeterminate like this, then also it can be done, only it will involve little bit more analysis, not very complicated. Mass matrix is a diagonal matrix and finding the masses is very simple, it is just by observation, and calculation of this term is also a straightforward simple calculation. Thus, we can solve or get the approximate value very quickly. Here the advantage may not be very clear, but if you have a 10-degree freedom system, you will find that this is a very quick method compared to the method what we have discussed earlier. Now, let us take up the other method. This is an extremely important approach, and we will refer to it at a later stage also, but understand the case here. Now, under normal mode oscillation condition, we have seen that all masses are oscillating with the same frequency and almost they are either at same phase or exactly opposite phase. It means that each mass attains its maximum speed at the same instant of time, which is the maximum velocity of that. So, if the normal mode can be represented like this, then xi dot is velocity and this maximum value of the speed of each one is because maximum value of sin omega t can be only 1. Similarly, all these masses, they attain their extreme position, that means which represents the extreme stretching of all the elastic members, or if there is gravity, then the extreme position in the gravitational potential energy well. So therefore, that will be, we know that extreme positions are all equal and they are attained at the same instant, and the values are nothing but the capital Xi. So that is also quite straightforward. Because maximum value of cosine omega t is 1. So now, what will be the maximum kinetic energy of the whole system? The maximum kinetic energy of ith mass will be half mi into velocity is this, the square of that is going to be half omega square mi xi square. So, for all the total kinetic energy of the system will be just sum of all this if there are n degrees of freedom or n masses, will be this. Now, this can be in matrix form, can be written like this. This is straightforward demonstration of this. I am avoiding it, but you can easily expand it and find out that this is nothing but this. Similarly, maximum potential energy of the system that will be half, each one will be in the stiffness matrix. If the stiffness matrix be K, then this can be also easily seen through little bit analysis, that total potential energy maximum for this system will be, where K is the stiffness matrix. So now we know that for a conservative system where there is no dissipation, now when the kinetic energy is maximum, potential energy is 0. Similarly, when potential energy is maximum, kinetic energy is 0. So therefore, both of these two must be equal to the total mechanical energy of the system, and so they must be same. That we have used even in the solution of single degree freedom system. So now, remember, all these things what we are doing, we have not mentioned, that is all during actually a case of normal mode oscillation. Then only this is valid. Then only they will be all attaining 0 velocity at same instant, maximum velocity at the same instant. So though we are not showing any I here as the particular mode, but this is valid for only natural mode oscillation. So therefore, if it is natural mode, we can show like this, or J mode. can always do that, and frequency obviously is big. So therefore, for for the first mode, omega n1 square can be expressed as because then it will be natural mode A. Now, Rayleigh's principle says that if we assume a column matrix X as the first natural mode and evaluate this quantity, we will get a quantity which we call as Rayleigh's quotient. So, Rayleigh's quotient R is for an assumed mode shape X, which transpose A X, which need not be exactly same as the first mode, and divide this by this quantity, then R tends to omega n 1 as X approaches the first mode. The most important thing is, and this it will approach from the higher side. And when the assumed X becomes identical with the actual first mode, then R becomes equal to omega n. So therefore, for an assumed shape X, whatever value of the Rayleigh's quotient we get, it will be always slightly higher than the real natural frequency. Of course, I must say R is not because this is omega square. So, determination of the fundamental frequency using Rayleigh's principle will always give us an upper bound. There is another very important point to be noted here, is that the value of Rayleigh's quotient, that as it is nearer to omega n 1, is somewhat insensitive to the choice of X. That means even if the choice of X is somewhat different or quite different from the first mode, the value of this quotient will be somewhat nearer to this. That means a large error in X will not be reflected as a large error in this natural frequency. So therefore, R is also So now let us solve the same problem using Rayleigh's technique. So Rayleigh's technique says this is Dunkerless. And the Rayleigh's will be so let us find out what we get for solving the same system. Now, as you can see, we will need the K matrix and the M matrix. M matrix is quite straightforward. So let us solve the example. The same example. So to find out the K matrix, best way for us will be to derive the equations of motion. So for mass 1, the forces acting are for mass 2, which is M, for mass 2, which is 2M, forces, this force will be same as this, and for mass 3, which is again M, the force acting to this thing in this case. So the equations of motion can be written for the 3 masses will be, this one will be M x1 2 dot is equal to 2M x2 2 dot for the second mass, and for the third mass so now we rewrite them in a manner, and for normal mode oscillation so that cosine omega t term will go from every place, and let us rewrite in a manner so that we can omega square M x1 plus 3k x1 minus 2k x2 plus 0 x3 0. This one will be 2 omega square m. I am writing capital X, so for it this will be then x2, and here this one x1 term will be plus a x1, x2 term will be 2k x1 term will be also plus a x1 minus and plus a x3, and the third one will be minus omega square m x3. There is no 3 minus x2, I have made a mistake. So x1 will be minus 2k x1, x2 will be k, so 3, so plus ek, and x2 will be minus. So for this one, it will be no x1 term, it will be 0 x1. For x2, it will be minus minus plus. When it comes to this side, it will be minus k x2, and this comes to k 3. So we are not interested. This is okay. This will be simply the mass matrix. So this becomes minus omega square m x plus k x equal to 0. This is a set of equations in matrix form. So obviously this is nothing but this m 0 0 0 2 m 0 0 0 m plus, now K matrix you will find will be so it will be 3, K will come here 3 minus 2 0 minus 2 3 minus 1 0 minus 1 1. So the K matrix now, M matrix is this, and K matrix is this. Now comes the application of this, the choice of X. It is true that we will assume some value of X. Now if we make the choice somewhat logical, then obviously the results are going to be better. Otherwise, if we take some extremely wild choice deliberately, we will get something nonsense. So here when it go in the first mode, you will find the inertial load here is proportional to m, here it is proportional to 2m, but not exactly, because the amplitudes are different and amplitude here is more. Again here it will be. So therefore, everywhere you will find the force acting is somewhat related to the mass, and the deflection is also related to the stiffness. So one quick way of having a reasonable assumption is, let us see that what is the stretch of each position or displacement at each position due to a gravitational pull. That means if we hang it, what will be the deflection of these in the static equilibrium position. So that is one very common technique used. So gravitational deflection, if we, that means if we hang, what will be the x1? X1 will be something like mg, 2mg and mg. We do that. So therefore it will be, I think detailed calculation I will not do. So here it will be 4 mg by k, x2 will be 11 mg by k, x3 will be 13 mg by k. So we can take it will be 1, 1.38, 1. It is in that ratio 4, 11, 13. If we divide by 4, first one will be 1, second one will be 1.38 and 11. So in this ratio. So let us use this as first mode. This is just due to gravitational deformation. So using this, we get, I will not calculate the whole thing. R is going to be k by m and 1.35 is top and 7.47 the numerator. This becomes 1.35, this becomes 7.47 after you take the k and m terms out. And this will be equal to 0.181 and R is actually supposed to be square of the natural frequency. So first natural frequency you get is approximately equal to square root of this becomes 0.425. Now this is extremely revealing, because even using an approximate method to choose the first mode by just using the gravitational pull and the subsequent deformation, the natural frequency we get arrive at is very close, rather almost same, but there may be difference in the higher order position, third, fourth, fifth place. So you can see how accurately you can get. Now again, to demonstrate that, as I mentioned, that this value accuracy is not very sensitively dependent on the correctness of the choice of this. So if I now say, let us have some quick method of finding out this. So, even for finding the gravitational pull and doing that, we had to do some calculation. But even if we just by observation, so let us say that let x1, x2, x3 be, say let us say we say it is 1, then this one being is being the same force if we apply everywhere, for example, then this will increase by another half amount of this. So, let next one will be 1 plus half of it, so it will be 1.5. The other one again we approximately say another half will go, so therefore we may say 2. This is a very crude way of lecturing, as you can see. If you use this, you will get Rayleigh's quotient as k by m into 1.75 by 9.5 equal to and this will result in approximate value of this. So, surprise that even if we made such a crude way, we assume the mode shape, you can see it is only in the third place the error is coming. So, this is the actual merit of Rayleigh's principle, otherwise just this expression is not the real thing, but it is actually the insensitivity to the errors in the choice of x in the result, that is the main merit of this Rayleigh's principle. And as you have said that you will always get, here it was very close, so you did not see the difference, but here you can find we have made some errors in the choice, more errors compared to the previous one. This was also a static deflection case, it is not the actual mode. This is not the real mode. Real mode we have found out in the previous lecture, you can compare and find out what was the real mode. But even if you make this, you get some value, but which is always more than the real value. That is why we get always an upper bound. Why? The proof that why it is an upper bound, etc. Those that proof can be found in standard text, and I did not devote time to that proof, but the procedure, if we understood, will be good enough. So, thus for designers, the quick way of estimating the first natural frequency of even of a complicated system can be done without going to computer and running a whole program, just by this some approximate method which gives some idea. So, therefore, if we say that this is the Dunkerley's method and this is say the Rayleigh's method, then we know that it must be between this and this. So, we narrow the gap and the designer can satisfy whether this is in the dangerous zone or not. That means whether there is any excitation from outside possible somewhat near this